So hopefully now you understand how this continuous spectrum of electromagnetic radiation is created in the sun. But let's talk about what happens when it leaves the sun. So we know that it's been emitted, we have these photons of light, but what exactly is light? Well, for a long time, scientists thought it was just a smooth and continuous wave. But it was Albert Einstein who figured out that when this light interacted with matter, specifically with electrons, that it would take on a different character. In fact, it behaves as though it's composed of something that has mass, like individual bodies of particles. And so he called these photons. So really, light is a particular kind of matter. It's a photon that behaves like a wave. So it has some wave-like properties, and let's take a look at that. As these photons move through space, they essentially have two fluctuating fields. They have this electric field that fluctuates like a wave, and then they have a horizontal magnetic field that fluctuates like a wave. Before we get too deep into wave theory, let's see how NASA can explain electromagnetic radiation. Might make it a little bit more clear.
Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
That was a lot of information. So just to summarize some of the key concepts from that video, we talk about different electromagnetic radiation regions in terms of their wavelength, which was really just the distance between their successive wave peaks. And you'll see this symbolized with the symbol lambda. And we also heard in there that they can range from very long, and they would be reported in units of meters, down to very, very short gamma rays that would be reported in either micrometers or nanometers. So this can be confusing, and we should spend a little bit of time reviewing these metric scales. When we take measurements ourselves, we usually think in terms of meters, centimeters, or even millimeters if we're really particular about our measurements. But when we're talking about wavelengths, we're much more often in the realm of micrometers or nanometers. And for perspective, there are 1,000,000 micrometers in 1 meter and 1,000,000,000 nanometers in 1 meter. So that should give you just a little bit of an idea of how small we're talking here. And to be able to convert from one to the other, again, this should take you right back to high school science. If you wanted to convert from micrometers to nanometers, you would simply have to multiply it by the difference between these two, so 10 to the negative 3, or essentially divide it by 1,000. The video also pointed out another way that waves are typically described, and that's in using the frequency. So the frequency is defined as the number of peaks that pass a fixed point per unit time, and the most common unit for that is the hertz, which is essentially how many peaks would pass a fixed location in 1 second or per second. Now, we don't usually refer to the frequency when we're talking about remote sensing, but that is much more common when you're dealing with sound science and the interpretation of waves as sound. So while we typically use wavelength to describe electromagnetic radiation, and sound scientists use frequency, you can very easily go back and forth between the two because they're inversely related to each other. And this is because all electromagnetic radiation travels at the same speed, the speed of light, which is 3 times 10 to the 8th meters per second. And so since they're traveling at the same speed, if you were to have a higher frequency, it would automatically require that you have shorter wavelengths since the speed remains constant. On the other hand, if you have longer wavelengths, you're going to have a lower frequency. So essentially, when we say these are inversely related, it means that as one goes up, so as the wavelength increases, the frequency inherently has to go down because of this constant speed of light. The wavelength is also inversely proportional to the amount of energy that's contained in each of these photons. So the longer the wavelength, remember longer wavelength means lower frequency, also means lower energy is contained in that photon. Think about radio waves. Whereas these shorter wavelengths, higher frequency wavelengths, are much higher energy as well. So with these metrics of wavelength and frequency, we can describe energy across the entire electromagnetic spectrum, which extends from these very short gamma rays to these very long radio waves. The region that our human eyes can see, the region of visible light, extends from just below 400 nanometers to just about 750, close to 800 nanometers. The really interesting part is that the exact sort of start and end of what we call this visible spectrum depends on the person as well. If you think about it, some people can hear certain wavelengths better than others. It's the same with the visible light. So we all may not perceive color in exactly the same way or be able to detect subtle differences in color. So hopefully now you understand a little bit more about electromagnetic radiation, that it's a form of energy that exhibits wave-like behavior, but also consists of a mass-like photon, and it carries this energy through space to the Earth, and when it contacts materials, this energy interacts particularly with electrons of surface materials. And this is really what we're interested in, is the transfer of this energy, or what happens to this energy when it contacts objects on the ground. It's only because of this differential response of various materials to electromagnetic radiation that we can use remote sensing at all to gain information about objects on the ground. So let's talk a little bit about what those interactions look like with the surface. So essentially, when electromagnetic radiation reaches the Earth's surface, there are three types of interactions that are possible. So here's the surface material, and here are your wavelengths. And we call this incoming radiation irradiation. So the irradiation can either be reflected back, and we call this radiation. It's radiated back. It can be absorbed by the surface material, or it can be transmitted through the surface material. And the ratio of how much each of these different interactions occur is dependent upon both the nature of the surface material, but also of the wavelength. So different wavelengths will be reflected or absorbed or transmitted in different proportions for even the same material. And the important thing to keep in mind is that energy can't be created or destroyed. So what is incident, this is that irradiation, so what actually strikes the surface has to be the sum of all that's reflected, all that's absorbed, and all that's transmitted. We'll break these each down a little bit further. When we're talking about reflection, we're referring to a radiant energy that strikes an object and just rebounds completely unchanged. So the wavelength is not changed, the amount of energy is not changed, it's literally just reflected back. Now how that light is reflected back depends upon the texture as well as the composition of that surface material. And so when we talk about reflection, if we have a very, very smooth surface, as we call this specular reflection, the angle of incidence is equal to the angle of exit. Right? So we can imagine that this is what you might see with a mirror, a very smooth surface. But unfortunately, most materials on the Earth's surface are much more coarse. They have a very rough surface area. And what happens with that is we end up seeing much more of a scatter of what we call diffuse reflection. So as the photons strike each of these surface materials, they're being reflected back at different angles because of the angle of the original surface material. When electromagnetic radiation is absorbed, or at least part of the energy from that photon is actually transferred to the object. Typically, it's converted to heat and then re-emitted from that material at a longer wavelength, typically in these thermal or infrared wavelengths. Remember that how light interacts with matter is dependent upon which wavelengths you're talking about, and water is a really cool example of that we can see with our own eyes. So with water, longer wavelengths, which are lower energy, are typically absorbed pretty quickly, so they're absorbed at shorter depths. But these much shorter wavelengths with higher energy, they're able to penetrate deeper into the water column. And in fact, the blue wavelengths can penetrate up to about 100 meters of depth. And that's why if you go deeper and deeper into the water becomes a bluer and bluer shade, whereas at the surface it may seem more of a sort of a muddled bluish color. And again, that's because by the time you get down deeper in this water column, you've exhausted all of those reds and greens and yellow wavelengths, and you're left with nothing but the blue. And in fact, if anyone's been scuba diving, you will know that the color that you see when you are that deep in the ocean is a color that you never see on the Earth's surface. It's really quite amazing. Transmission was the third type of interaction between electromagnetic radiation and surface materials. And just like reflection, with transmission, the energy is passing through the object and it remains unchanged. So the wavelength and the energy remain unchanged as it passes through the object. However, the angle of exit may be altered depending on the composition of the object. And we've seen that when you put a pencil in a water glass and it doesn't look like the pencil is connected to itself anymore. It's not that the wavelengths or the colors of that pencil have changed, it's just how it's reflected back that changes. Modern technology uses this differential absorption of surface materials to create things like windows that will allow through visible light so that we can see into a room, but that will reflect back those longer thermal wavelengths. In particular, this is really useful in warmer climates where they're trying to avoid solar overload inside buildings. Because our sensors aren't typically inside of the surface material or below it, it's the reflection that remote sensing is interested in. But to understand what we really mean by reflectance in terms of remote sensing, we need to get a couple of basic definitions under our belt. We've already mentioned irradiance, right? When we were talking about the sun and the energy coming, the electromagnetic energy coming down from the sun to the surface, that was the irradiance. In other words, it's the radiant flux, or how much energy is coming in and is incident or hits a given surface area on the ground, and that's usually in terms of meters squared, and the radiant flux, or the amount of energy, is usually in terms of watts. So when we talk about irradiance, we're talking about the watts per meter squared of radiation that is hitting the surface. And then we know that that irradiant light is going to come in and interact with the surface, and then there's going to be a certain proportion of that that is reflected back. So we talk about excidence as how much of that energy leaves that same unit area on the ground, but in any direction, right? So when we're talking about excidence, we're saying that the surface is likely not entirely smooth and that there are probably millions of photons that are hitting that small meter squared area on the ground. So how much total energy, radiant flux, is emitted back in all directions from that unit area? Again, this is in watts per meter squared. But a sensor can't measure excidence because a sensor isn't everywhere, right? Typically a sensor is in one location, and so it's only able to detect the radiant flux leaving that surface on the ground in the direction heading towards it, right? So in other words, if the sensor is floating somewhere out here, if you can see my mouse, okay, that irradiant energy, that irradiant flux coming in, it's going to have a certain proportion of that that is exiting, right, in a certain direction. That sensor is only going to be able to detect that which hits it. It's not going to be able to quantify all of the excidents in other directions. And so when we're talking specifically about just what the sensor can see, so in other words, it's how much energy is emitted in a given direction, that's referred to as radiance. And this radiance is actually what the sensors are recording. How many photons are hitting the detector, which is in a given spot, for a given unit area on the ground. And this is a common point of confusion. We have to remember that the sensors are not directly measuring reflectance. They're actually measuring the radiance, right? How many photons are exiting in a given direction. And in order to know what the actual reflectance is for a given wavelength, we also have to know how much energy there was in the first place that hit the surface. So to calculate reflectance, we actually have to take what the sensor is detecting, that radiance, and divide it by the irradiance, or the amount of energy that was incident upon that surface material in the first place. And there's a very complicated formula for this, but luckily we have software packages that will calculate this for us. So how do they do that? Essentially, they're taking that measured radiance from the sensor, and then they're taking a whole bunch of other variables that quantify that irradiance, or how much energy there actually was incident upon the surface. Irradiance is modeled for each wavelength based on what we know the sun is emitting, right, in the different wavelengths, and then also a whole bunch of settings that describe the location where the radiance was collected. So the location on the Earth, the time of day, the date, so that we can find out what the solar zenith angle was, how far the sun was from the Earth, how much atmosphere there might have been between the sun and the Earth's surface. And so all of these different variables are essentially used to model how much of incoming light there actually was that hit the surface. All of that sounds pretty complicated, but maybe the most important take-home message is that reflectance really is just a ratio of how much energy is reflected based on how much total energy there was in the first place. And this ratio is really dependent upon several things. First of all, it's going to differ across wavelengths. So some wavelengths will have a higher ratio that's reflected back compared to the total incoming. It also depends on the surface texture or structure, right? We talked about how you can have specular reflectance if you have a very smooth surface and everything in its full intensity is directed back in one direction. And this is really common. If you think about times you've been in an airplane or been on the water and or had a car's mirror in front of you, and the sunlight hits that and it blinds you because it shines right back on your face. This is an example of specular reflectance. Most light is reflected in a diffuse manner from surface materials, but this is also going to impact that ratio, because remember, we're talking about the reflected energy in a given direction, in other words, where our sensor is. Illumination is also an important part of it. So we know that if we have some materials on the ground that are being shadowed, either by topography or other structures, that ratio of reflected to total is going to differ. And then also the atmosphere plays a really large role, which we'll get into in the next video a little bit more. We'll get into a little bit more detail, but just to summarize, remember, it really is this property that surface materials will either reflect, absorb, or transmit light differentially, and that this varies not only across surface material type, but it varies by wavelength within a given type of material. And so what's really interesting, and what gives us the power to discern different objects, even though maybe, for example, to our visible eye they may look very similar, is that some objects that may be indistinguishable in some wavelengths are actually very distinct in others. For example, consider this one shot here over a surface with both water and vegetation in developed areas, and you can see the various bands represented here, from blue all the way through the mid-IR. And while in some bands you can see that, for example, blue is reflected back from the water, once we get into these longer wavelengths, they're much more readily absorbed by the water surface material, and therefore there's less to reflect back and they appear darker. Other objects, which are very obvious in one particular wavelength, may be unidentifiable or indistinguishable in a different wavelength. And this is really what we use to determine information about these various surface features. It's sort of interesting to think about this relationship between what's absorbed, transmitted, or reflected, because you can speak of this in terms of that it's absorbing a large amount of near-infrared wavelengths, or that it's not reflecting. So they're all related. They all have to sum to the same total amount of incident energy. But it's not just the physical and chemical characteristics of the surface material that determine how energy is reflected back to the sensor. We talked briefly how also the texture of the surface can also impact the reflectance that's received at the sensor. So really it's this sort of geometric structure of the surface that can affect how much light arrives back at the sensor. And just like with reflectance based on chemical or physical characteristics, how this light is reflected geometrically is also dependent upon the wavelength. And that's because the texture or the amount of roughness that you have for your given surface material is going to impact different sized wavelengths. Essentially, smaller wavelengths can be scattered and diffuse reflected by very small variations in that surface texture, whereas the longer wavelengths tend to be scattered only by larger variations in surface roughness. Most natural features do have some amount of texture to them, and we refer to them as a Lambertian surface. And again, this is typical for natural materials. And we would expect that these Lambertian surfaces would reflect light in a diffuse manner. So in other words, because of those geometric variations in the surface, as light strikes it, it's going to be reflected back in all different directions. Right? But you can have instances where you have a pure specular reflectance, very smooth surfaces this will happen with, and again it's common for mirrors and also water bodies. So there the angle of incidence is the same as the angle of excidence. And just to help you visualize that, here would be your perfect specular reflector, right? And most natural features fall somewhere in between that perfect specular and this perfect diffuse Lambertian surface, right? We're usually somewhere in between where there is a dominance of reflected light in a given direction at that angle of incidence, but there's also this diffuse reflectance in addition to that. A great example of something that can be both a diffuse reflector and a specular reflector, depending on where and when and the conditions, would be water. So here we're looking at Burlington and Lake Champlain, and these regions of very high reflectance, we're essentially seeing very smooth water here, and that angle of incidence from the sun is just right so that when it strikes this surface in this location, it exits at the exact same angle back to the sensor in very high quantities because it's specular reflectance, and all of that incident energy is reflected back in one common direction. So this is really what we think of when we talk about sun glint. But there are other regions where either the water was a little more choppy, or maybe the water had more particles within it, or maybe it's just that the location of the sensor is not right to pick up that specular reflectance from these other locations. It really is just right there that the sensor is getting that direct hit from the specular reflectance. But it is really interesting when you see these patterns, and if any of you do end up choosing to work on the project and select areas with water, you're likely to see this variability within water, which can make it kind of hard to classify water if you're looking at particular wavelengths. So remember, some wavelengths are not reflected as much as others, and so you might choose a different wavelength that doesn't have high reflectance in the water to remove that effect. Reflectance can also be complicated by topography, and it's obvious when you think that shadowed, like completely shadowed areas are going to have different reflectance than sunlit areas. But it's actually even a little bit more complicated than that, because what ends up happening is when you have these surface materials that are directly facing the sensor, so that when light strikes it, it does have some specular qualities that reflect it back directly at the sensor. Those are going to appear much brighter than surface materials that are slightly angled, because remember, we talked about how most surface features are some combination of specular and diffuse. And so what that means is that if we have a surface that is aimed so that most of this highest intensity reflectance, which includes some of that specular reflectance, is aimed at the sensor, those areas are going to appear brighter even if they're not in actual shadow. Later in the semester, we'll talk about some different ways that we can compensate for that, so that materials that we know are similar, say for example this hillside over here and this hillside over here, but are looking very different spectrally, how we can compensate for that if we know something about the topography of that region. So that will wrap up sort of the basic concepts. We'll look at some specific surface materials and how different wavelengths interact with those in our next video.